Welcome back to Honors Calculus. In this video, we're going to be looking at some applications of the definite integral. We'll start off with an application we've already discussed in this course. The path that led us to the integral in the first place was investigating the area bound between the curve of an arbitrary function and the x-axis. Now that we have more sophisticated tools for actually calculating the integral, and we don't have to rely on the summation notation and going through that whole process, we can take this idea and make it a lot easier to work with. So let me get my head out of the way, and let's take a look at the equation y equals x cubed minus 9x squared plus 23x minus 15. We can work out and graph this equation in detail if we would like to, but I just want to get enough information to figure out how to set up the integral. I'm not going to go into the algebra of dividing out and factoring, but this can be factored. And in fact, this particular equation factors to x minus 1 times x minus 3 times x minus 5. And so sketching out our graph, we can find that the y-intercept is somewhere down here. It's at negative 15. Where that is, I don't really know. We have x-intercepts at 1, 3, and 5. They all have multiplicity of 1. So we're going to pass through looking something kind of like that. And to calculate the area, we'll be looking at the part here, and we'll be looking at the part here. To look at the part above the x-axis, we can set that up. I'll call that A1, and I'll call this down here as A2. A1 is going to simply be the integral from 1 to 3 of the function x cubed minus 9x squared plus 23x minus 15 dx. A2 is a little bit trickier. We saw previously that when you are looking at an area below the x-axis, that the calculation actually comes out negative. And there are applications where that's important, and thinking about that as a negative area is important. But we want to calculate here the planar area of this shape in the geometry sense. So in order to do that, I'm going to introduce a negative on the integral from 3 to 5 of the same function, x cubed minus 9x squared plus 23x minus 15. And then to find the total area, we can simply add these two things together. All right. So starting with this one, this is a simple polynomial, and polynomials can be integrated using linearity and the power rule. The integral of x cubed is 1/4 x to the 4th. The antiderivative of x squared is 1/3 x cubed. The integral antiderivative of x is 1/2 x squared. And integrating a constant gives you a factor of x. If we needed the indefinite integral, we would put a plus c here, but we're doing a definite integral, so we don't need to bother. So we evaluate this at 1 and at 3. We can simplify some of these fractions first if we want to. And so we evaluate. 3 to the 4th power is 81. 3 to the 3rd power is 27. 3 squared is 9. And then evaluate at 1. 1 to the 4th is 1. 1 cubed is 1. 1 squared is 1. And 1 times anything is that thing. So we've got 81 over 4. We've got minus 81. Let's see, 23 times 9 is going to be 207. 15 times 3 is 45. Then distributing this minus, that's minus 1/4. Minus a minus is plus 3, minus 23 over 2, and plus 15. We could look for common denominators immediately, but this is actually going to be easier. Noticing where we do already have common denominators, 81 over 4 minus 1/4 is 80 over 4, and we'll be able to divide that. 207 over 2 minus 23 over 2 is 184 over 2, and we'll be able to divide that. And then we'll just deal with the constants, or the whole numbers. Minus 81 and minus 45 is minus 126. Plus 3 is minus 123. Plus 15 is minus 108. So we've got 80 divided by 4, which is 20. 184 divided by 2, which is 92. 20 plus 92 is 112. 112 minus 108 is 4. Then we look for the second area. Remember, this is the area just of the first part, worked out to a whole number, which is a little bit surprising, but we will take it. And then I want to do the second integration, which is so similar to the first that I'm just going to copy these first couple of lines. And modify as necessary. Right, to find a2, we want to take the negative, and instead of having limits of integration at 1 and 3, we wanted limits of integration at 3 and at 5. But the actual integration works out exactly the same, just changes the limits of integration. So it changes what it will look like when we evaluate. 5 to the 4th power is 625. 5 cubed is 125. 5 squared is 25. And then we have the 3's, which are actually something we already did. 3 to the fourth is still 81. 3 cubed is still 27. And I kind of ran out of room for the 15 times 3 at the end of that line. But it'll make sense when I actually do the calculations in the next line. All right. But we have 625 over 4. We have 375. We have, let's see, 23 times 25 is going to be 575. And 15 times 5 is 75. 1/4 times 81 is 81 over 4. Then we have 81. We have 207 over 2. And we have 45. Distributing the subtraction sign. We, again, could set this up and try to get these fractions to cancel each other out, but I'm going to cross my fingers and hope that everything will work out nicely. Negative 625 over 4 plus 81 over 4 is going to be negative 544 over 4. Negative 575 over 2 plus 207 over 2 is going to be minus 368 over 2. And then we have the whole numbers. 375 and 75 is 450. 450 minus 81 is 369. 369 minus 45 is 324. Let's see. 544 divided by 4 is going to be 136. 368 divided by 2 is going to be 184. Minus 136 and minus 184 is minus 320. And minus 320 plus 324 is exactly 4. And so that's the area of the second region. And finally, to wrap everything up, the total area was the area of the first region plus the area of the second region. We get that the area bound by the curves and the x-axis for this particular graph is 8. Changing gears, if we want to look at a different situation, integrals came about by adding up lots of little pieces. And so applications involving adding up lots of little pieces are really great for modeling as integrals. The relative mass in pounds per inch of a tapered rod measured a distance x inches from the narrow end is given by d of x is 1/2 times the cube root of x. And our instructions are to determine the total mass of such a rod, which is 12 inches long. So we have here this idea of probably rounded to some extent, but some sort of a spike, perhaps, that can be used for securing a tent or a guy wire to a pole or something like that. And we know that the total length of this rod is 12 inches, and we have the relative mass. Another way of calling that is the linear density. If we treat this stake as a one-dimensional object, then its density depends only on its position in one dimension instead of in three-dimensional space that an object actually takes up. But density is the mass in an infinitesimally small piece of the object. And the total mass asks us to add up the mass of each infinitesimally small piece. And as I said, integrals are perfect for adding up infinitesimally small pieces. So the total mass here should be represented as the integral. We start at x equals 0, we go to x equals 12. That's from the start of the rod to 12 inches down the rod, of the density function 1/2 times the cube root of x integrated with respect to x. Right? The integral is asking us to add up each little piece of the mass of this rod. And as integrals go, this one's not that bad. It's a simple power function. We can take the 1/2 out in front. Cube root of x is x to the 1/3 power. And the antiderivative of x to the 1/3 using the power rule, 1/3 plus 1 is 4/3. So we'll have 1 over 4/3 times x to the 4/3. And we will evaluate that at x equals 0 and at x equals 12. 1/2 times 1 over 4/3. 1 over 4/3 is 3/4. 3/4 times 1/2 is 3/8. And then we have 12 to the 4/3 minus 0 to the 4/3. 0 to the 4/3 is 0. So we have here 12 to the 4/3, which is the same thing as 12 times the cube root of 12. We can cancel out a little bit here. 12 over 8 is 3 over 2. Multiply that by 3, and we get 9 times the cube root of 12 over 2 as the simplified version of this mass. Right. An answer only a mathematician can love, but that's how we like it in math class. The mass of this rod is 9 cube roots of 12 over 2. Going back to the idea of area, I would like you to calculate the area of the curve y equals x squared minus 5, not the entirety of it, but a portion of this curve between x equals 1 and x equals 2. So calculate the area of that region, see what you come up with, and I'll see you next time.